So hello everyone, just wait 1 minute, we will start. Okay, so we will first um, so first we will just solve the first 4 assignment questions, then we will start starting about the quantum cryptography and teleportation a little bit, okay? After just solve the first four, it will be quickly done. Then quantum cryptography and teleportation, okay? Wait, then my videos is done. Okay. So first question is like this is the first one. Choose the correct option that must be followed by zero for a bipartite system A plus B. I think this is already done in the class. So here only B, C and D will be the correct option. Okay. So B will be correct. B, C and D. These are the correct option. Okay. This cloning one also like nothing to do here. So last one is correct. Okay. It is not possible to clone an arbitrary quantum state. We'll see also later the cloning theorem. So let's do the third one. Okay. Choose the correct option in the context of Bell state from the following. All Bell states are maximally entangled, right? So this is true. Mhm. Okay, so all Bell states are maximally entangled. The second one, partial transpose of the density matrix for the Bell state has negative eigenvalues. Is it true or false? So it may have negative eigenvalues, right? So it is also true. A and B are correct. And we have to calculate von Neumann entropy. The option C, 5 plus state is given, 0, 0 plus 1, 1, right? So we were given the 5 plus state is 1 by root 2 0, 0 plus 1, 1. So for the entropy calculation, what you have to do? You have to first calculate the density matrix, right? Corresponding to this 5 plus state. So rho will be given by 5 plus 5 plus, right? If you do this, what you will get? 1 by 2 0 0 plus 1 1 0 0 plus 1 1. Now if you do this, you can write like 1 by 2, it will be 0 0 0 0 plus 1 1 0 0 plus 0 0 1 1 plus 1 1 1 1. Now you can write it in the matrix form, right? Let's hide this. If you write this in a matrix form, what will be the matrix? So 0 0 0 0. So this term is 1, right? Then 0 0 and 1 1, right? So you write like this, right? 0 0 0 1 1 0 1 1, right? And here also 0 0 0 1 1 0 1 1. So 0 0 0 0, right? both is 0, so this is 1. This is like 0 0 0 1. Is this term there? Nothing is there, right? So this term is 0. So this is 0. Similarly, 0 0 1 0. First term is 0 0, second term is 1 0. This is also absent, right? So this is 0 also. And this is nothing but first term is 0 0, second term is 1 1. So this is there, right? 0 0 1 1. So this is 1. Here the first term is 0 1. First term is 0 1. No, nowhere is first term is 0 1. So whole row is 0. Right. Third is first term is 1 0. First term is 1 0. Again there is no first term, that is 1 0. So here the whole row is again 0. And last one is first term is 1 1 and second term is also 1 1. First term 1 1, second term 1 1. So only this is there. Okay, that's how you write the matrix form of the row. Now what you have to do, you have to find the eigenvalues of row, because you need to calculate the entropy, right? And entropy is S row is given by minus sum over I lambda I log 2 base lambda I, right? So lambda I is the eigenvalues of row, right? Now we calculate the eigenvalues. What would be the eigenvalues? Eigenvalues will be determinant of 1 minus lambda should row 41 be 1. Uh, yes, sorry, this will be 1 also. Correct, this is 1. Because this time is there, right? 1 1 0 0. So let's calculate the eigenvalues, right? So 1 minus lambda 0 0 1. Okay, you keep the half inside. Okay, so half minus lambda 0 1 0. This will be minus lambda 0 0. Right? And this is 0 0 minus lambda 0. Again 1 0 0 half minus lambda equals to 0. And it will be first term is half minus lambda into determinant of this determinant, right? Minus lambda 0 0 0 minus lambda 0 0 0 half minus lambda, and this is plus minus, right? Again minus 1 into, again this is plus minus, right? So minus 1 into this determinant, right? This determinant is 0 minus lambda 0 0 0 minus lambda 1 0 0. this is equals to 0. Okay. Now if you solve this, then half minus lambda, and just writing these lines. From here you will get minus lambda into minus lambda into half minus lambda minus lambda square equals to 0. You just solve this equation and you will get lambda equals to 1 0 0 0. Okay. If I get time, I will do later, because otherwise you just solve, you will get this. Okay. Then you just put in the S row, you will get. Okay. S row will be minus sum over lambda I log 2 base lambda I, right? So this is 0, right? So C is incorrect, right? They are telling S row, sorry, S row is 1, but S row is 0. Okay. Von Neumann entropy is 0. And again you have to calculate the S of row 2, entropy of the second qubit system. S of row 2 you have to calculate, right? So row 2 would be what? Row 2 is nothing but trace over 1 of the density matrix row, right? So this is your density matrix. Now you have to take the trace over 1. Okay. Then what will be the row 2? What is the formula? You are taking the trace of over 2, right? Trace over 1. Sorry, you are calculating row 2, right? So second element, you have to just inner product, right? Sorry, trace you are taking over 1. So the what will be the row 2? Just see here, what will be the row 2? You know, row of A is A1, A2, inner product of B2, B1, right? This is for the first one, this is for the second one, right? So row of 2 will be given by, you keep the second element, right? This is for the first element A, you keep the second term and inner product over the first term, right? This will be your row 2. So here you see your row is this, right? So row 2 will be what? Row 2 is half of, you have to take the first term inner product, right? So 0 0, first term is 0 0, right? And keep this one plus first term is 0 and 1. So this is 0 and here it is 1. And keep the second term. So this is 1 0 plus again inner product over the first term. First term is here 1, here it is 0, right? So this is 1 this is 0. Keep the second term, that is 0, 1, plus again inner product over the first term. First term is 1 here, here also 1. So this is 1, 1. Keep the second term is also 1, 1. So this is your row 2. So this will be 0, this will be also 0. So your row 2 is, and 0, 0 is 1, 1, 1 is also 1. Right, so your row 2 will be half of 0, 0 plus 1, 1. Okay. So you write the row 2 in the matrix form. If you write it in the matrix form, similarly you can write, right, half of only 0, 0 and 1, 1 is there. So this is 2 by 2 matrix, 0, 1, 0, 1. Right? So this is your row 2. Again, you have to find the eigenvalues, and you will get S of row 2. Okay. Just calculate S of row 2. What will be the eigenvalues of row 2? That will be half minus lambda square equals to 0. Right. So lambda equals to half and half. So S of root 2 will be minus sum over lambda log 2 base lambda. Okay. So both are half. So we can write 2 into half log 2 base half. There is a minus sign, right? 2 to cancel. So it is log 2 base minus inside. So log 2 base 2. This is 1. Right. S of row 2 you will get 1. Okay. So S of row 2 is 1. So D is correct. So only A, B and D are correct. C is not correct because S of row is 0. Okay. Let's go to the final one, the fourth one. Fourth one, you have to calculate the concurrency of the 2-qubit state. And the state is given by this. Okay. State psi is given by this. Now concurrence formula we know, right? If your state psi is given by suppose A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1, then the concurrence of psi is given by 2 mod of BC minus AD. Okay, it is very simple. So in your psi is given as psi is equals to root 3 by 2 root 2 0, 0 plus half of 0, 1 plus half of 1, 0 plus 1 by 2 root 2 1, 1. Right. So here you know everything, right? So A equals to root 3 by 2 root 2, B equals to half, C equals to half, and D equals to 1 by 2 root 2. Just put the values and you will get the C. So C of psi 2 mod of BC. B into C is 1 by 4 minus AD, right? So this is root 3 by 2 root 2, 1 by 2 root 2. So 2 into mod of 1 by 4 minus root 3 by 8. So this is 2 minus root 3 by 4, right? So this is your C. Then it's okay, right? Then it's okay. So later we'll do some similar problems if we get time. So first I just want to say something about the cryptography, okay? Regarding the non-cloning theorem, all those things, okay? If any doubt here, just ask. Then we'll go to cryptography. Okay, fine. So let's go to so what is cryptography, right? What we do in cryptography actually, right? So suppose there is a person A, or normally in quantum mechanics we call Alice, and there is another person called B or Bob, right? And Alice has some message. Suppose Alice want to send some message, okay? Suppose there is one message. Suppose physics. Alice want to send this message physics to B securely, okay? That is, nobody other than Bob, nobody should know what the message is, okay? And this is what cryptography do, okay? So how A can send the message to B securely, okay? So first see how classically we can do the things, okay? Mm, Suppose uh, A and B both have some kind of structure or shape, some balloon kind of shape, okay? This is their structure, okay? Some instrument like, okay? So here Alice write um, So here Alice write like, okay, the same instrument, he just send the key to here like this, in this order. First row is this, second row, third row, and same. So the keys here, this the instrument. Okay. Hmm. What is this? Okay, so this instrument is the key here. Okay, the structure of the instrument. So first row, only B will know. B will have the same copy of the instrument. So A send here, and this is instrument is the key here, and B will get the instrument. So B will know how to read. Okay, he will read row wise. PHYSICS. Okay, sorry, there's one I here. SICS. Okay, other than A and B, nobody should have practically. Okay, but there is a problem. Like there can be some other persons who can have the same kind of instrument. Okay, so that's why we need the quantum cryptography. So in quantum cryptography also there is one key. Okay, so in quantum, suppose A wants to send the same message to B. The message is physics. So there will be some key, and this key, suppose the key is in quantum is 0 1. How many words are there? P H Y S I C S. Okay, 1 2 3 4 5 6 7. 0 1 1 1 2 3 4 5 6 7. So this is the key. Okay, so A and B will know the key. Other than A and B, nobody should know the key. Then this key will encrypt the message to some other words. Okay, so encrypted message will look like, suppose 0 keeps the P to P. Okay, suppose 1 change H to some H to B, suppose, and 1 changed Y to A. 0 keeps the thing same S, then again 1 1. So I becomes suppose C, then C becomes suppose D, again 0 keeps the same. Okay, this is the encrypted message. If some other person, this encrypted message can, everyone in the world can know. Okay, but nobody will understand. Okay, so B will also have the encrypted message. B is also in this world. Okay, so B can have this encrypted message. Everyone can have this encrypted message. So everyone knows that what A wants to send to B. A wants to send this encrypted message to B, but actually A wants to send the actual message is physics, but nobody knows that A wants to send physics to B. Everyone knows that A wants to send this PBA SCDS to B. Okay, SCDS to B, but only B can decrypt this message. Okay, because B also will have the same key. That is, B knows that what is the key distribution. Okay, then B will have the encrypted message. Then B will use this key 0 1 1 0 1 1 0. Then B start decrypting the message. Okay, decrypted message. So B will know the rules, right? B will keep the P to P, then P will become H, Y, S, I, C, H. Okay. So cryptography is all about how securely you can distribute the key. Because if other than A and B, if there is some third person, suppose C, or there is some if evil person, okay, C is the evil one, okay, if there is some third person who knows the key, who knows the key, then C can know the message. Okay, so cryptography is nothing but how securely you can distribute the key among A and B. Okay, so this is done in quantum cryptography. Okay, cryptography, because this key is the most important thing. Okay, if you know the key, you will know the message. Okay, that's why cryptography is all about secure key distribution. And nobody other than A and B should know the key. Okay, so this key sharing needs to be done in a secure manner. Okay, this encrypted message can be public, no problem, but the key shouldn't be public. So encrypted message, this message everyone can know, no problem. Okay, encrypted message can be public, there is no problem. Okay, but the key sharing should be done securely among A and B. Okay, so let's see how in quantum mechanics we do these things. Okay, suppose you have a horizontal polarized photon. Okay, and you measure the state in a HV basis. Okay, so this is your horizontally polarized photon and this is your vertically polarized photon, and you prepare the state in HV basis. Okay, if you prepare the state of the photon, prepare the photon state in HV basis, and you measuring in the HV basis. Okay, you prepare the first photon as horizontally polarized and second photon as vertically polarized in HV basis, and you measuring in HV basis. Now in HV basis you measure, and if you measure the horizontally polarized photon in HV basis, what is the probability of getting a horizontally polarized photon? 100%, right? If you measure in HV basis, you will 100% get H, because the state you prepared is H, and 100% chance of getting V, right? If you measure in HV basis. But if you measure in, suppose 45 minus 45 basis, okay? Measure in 45 degree minus 45 degree, or you can call it this diagonal or anti-diagonal basis. Then what will be your result, measurement result? You prepare the first photon in as a horizontally polarized, and if you measure in horizontally polarized vertical polarization basis, then you will 100% get horizontally polarized basis, right? Polarized photon as your measurement result. But here if you measure the same photon in anti-diagonal, diagonal, or plus 45 minus 45 degree basis, then what will be your measurement outcome? Probability of measurement outcome. What are the chances of how 100% chance, or how much is the chance of getting horizontally polarized photon in this basis if you measure? So fast photon horizontal, anyone can tell? So if you measure in plus 45 degree minus 45 degree, in this basis what will be your horizontally polarized photon look like? H you can write as 1 by root 2 45, or so this is your basis, just draw the thing. So this is your horizontally polarized basis, or you can call it zero state. This is your vertical polarization, or you can call it one state, no problem, whatever you want, okay? And this is your diagonal state or 45 degree, okay? You can call it as 0, and this is your anti-diagonal state, okay? Or minus 45 degree. You can call it at 1. So H you can write as this diagonal, you can call this 45, this is minus 45, okay? So you can write H as 45 minus 45 degree, okay? In this case, or you can write H equals to root 2 of diagonal minus anti-diagonal, okay? So if you measure the same H here in this species, so there is a 50% chance of getting H horizontally polarized. So measurement depends on the basis, okay, in which species you are measuring, that is important, okay. And this is important in quantum cryptography, that we will see. The basis is important, okay. Whether you are measuring in HV basis or in diagonal anti-diagonal basis, this is making 45-degree angle, okay. So that is important. And we know that we already know in entanglement that HV and plus 45 minus 45 degree, they are conjugate basis, like time energy or position momentum. Like them in polarization, this HV, okay, and diagonal anti-diagonal, these two bases are conjugate basis, right? And this conjugate basis, we know that what is definition of entanglement: simultaneous correlation into conjugate basis, right? Just saying. So measurement in which basis, that is important, okay. And another one that is already done in the class, just saying no cloning theorem, right? Because these two are important in cryptography, okay. No cloning theorem, but it tells that you cannot clone an arbitrary photon state, right? You can't clone an arbitrary photon state. Of course, you can teleport a arbitrary photon state, that is done in quantum teleportation, but that is not cloning, okay. Cloning means another Xerox copy you are generating. That is not a Xerox copy, you are just transferring it, okay. You can teleport the state, but you cannot clone the state, okay. These two are different. In teleportation we will see, okay. So that means, suppose you make some device, okay. This device is, you name this device U, and suppose you can clone a horizontally polarized photon, clone H. That means if you give horizontally polarized photon, you will get two horizontally polarized photon, okay. So suppose you can do this, you can do cloning of horizontally. Also you can clone a vertical photon also, suppose. And now you give a 45-degree photon, okay. And 45-degree means you give H plus V 1 by root 2. Now what it will do, it is equals to 1 by root 2. You can clone H, so you will make H, 2 copy of H, you will make 2 copy of V, right? But that is not equals to 1 by root 2 H plus V into H plus V, right? These two are not equal, this and this. That means this is nothing but 45 into 45, right? So you cannot do this. U45 not equals to 45 45, right? So there is no such device you can make that can clone your state. So that is basically the no cloning theorem, right? So let's go back to our cryptography. Okay. So we have Alice, and Alice wants to send some message to Bob, right? Okay. And there, okay, fine. So Alice is sending some photons to B, right? So there are two protocol. I will discuss only the BB84 protocol. Okay. So first thing is Alice and Bob needs to generate a key, right? So first step is they need to generate a secure key, right? That nobody should know, right? They need to generate a secure key. This is the first step. So that's so to do this, what they do, they want to generate a secure key that only Alice and Bob will know. No one else will know. Okay. So that's why first what they do. So that's what to do this. Alice first yeah, prepares the state in a randomly chosen basis and send the state to B. Okay. To do this, Alice first prepares the photonic state. Here we are dealing with photons. So he first prepares the photonic state in a randomly chosen basis. The basis can be HV or VH. This is random. Okay. In polarization, we have two bases. One is HV or diagonal, anti-diagonal. Okay. So here in the example, I saw that the first photon was prepared in HV basis, the state HV. Second photon is also prepared in HV basis, and the first photon was H, second photon was V. Okay, and H means 0 or V means 1, whatever you call. Or you can also prepare the state in diagonal anti-diagonal basis also. So that is random. So Alice randomly chooses his basis. Sorry, Alice randomly chooses her basis, and he sends the photon to B. Okay. So let's see how. So this is Alice basis. Okay. So and Alice chooses, suppose first photon Alice sent to B. Okay. This is photon. Alice is sending the photon to Bob. Okay. So Alice prepares the first photon in suppose diagonal anti-diagonal basis, okay, and he sends the photon to B, and suppose the first photon is 1, okay, Alice random bits, okay, Alice will send many photon to B, okay, so the first photon, so first time Alice decides to, that means Alice decides to send a photon in diagonal anti-diagonal basis, sorry, in HB basis, sorry, what am I, this is anti-diagonal diagonal basis, right? Sorry. So Alice decides that the first photon he will prepare in diagonal anti-diagonal basis. That he decides, and he decides randomly. There is no rule. She can decide whatever. Okay. So she decides that she will send the first photon in DA basis. She will prepare the first photon in DA basis, and also, sorry, whatever, and also she decides randomly that first photon will be diagonal. So what Alice did, Alice first chooses a basis randomly, okay. She decides that she will choose diagonal anti-diagonal basis or plus 45 minus 45 basis, okay. And again she decides that in this basis I will prepare the photon as a 45-degree polarized or diagonal, okay, whatever. And this is random. There is no rule. Whatever she wants, she can send the photon. Because Alice just needs to send the photon to B. Whatever photon she may decide. This is random, okay. So Alice prepare in plus 45 minus 45 or DA basis, and Alice also sends the plus 45-degree photon, and we call the plus 45 degree, we can write as diagonal photon, or you can write 1, okay, no problem. Sorry, diagonal is 0, right? Because this is your H means 0, V means 1, here it is the diagonal means 0, and anti-diagonal means 1. So you can write diagonal or 0. This Alice decides, okay. Second time Alice, the first photon is sent to Bob. Alice sent the diagonal photon or 0 in the diagonal basis. Second photon, Alice decides that I will make the photon in HB basis. The photon that Alice will send to Bob, that I will send to Bob, is I will make in HB basis, and the photon state will be 0 or horizontally polarized. Okay, this is random. Okay, there is no rule. Whatever she wants. Second, also she decides that third photon that she will send to Bob will be in diagonal anti-diagonal basis, and it will be again diagonal, or suppose this already diagonal, so whatever you want, it will be anti-diagonal or 1. Okay, like this. Third one HV1. Fourth one is this. Fifth one HV0. Sixth one HV1. You just write randomly, okay, no problem. So Alice sends this many photons, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And Alice prepares all these 11 photon state randomly. First photon he chooses the basis randomly, state random. Everything is random here, okay? She just send the photon to Bob. Now Bob will receive all these photons, 11 photons, right? So Alice decides her basis randomly, and also she decides the bits or photon state. Bits means 0 or 1, that means photon state, right? Also she decides the photon state randomly. She first randomly choose HV basis or DA basis. Then in HV basis, whether it will be H or V, that is also random. Okay. Now B receives the message, all these photons. Okay. Now B receives these photons that A sends to B. So A is sending these 11 photons to B. Now B receives this photon. Now B has to measure, right? After receiving. And after receiving the photons, B has no idea, right? B don't know, right? Anything. B just receives these photons. B has no idea in which basis Alice has prepared the photon. Alice has prepared the photon. Okay. B has no idea in which basis Alice has prepared the photon. B just receives the photon. Okay. Now B has to measure, right? The receiving. B don't have any idea in which basis Alice has prepared all the photons. Okay, first photon is prepared in HV or DA. B don't know. Second photon is prepared in HV or DA. That B don't know. B know nothing in which basis. B just receives the photon. Okay, B just receives the photon, and now he has to measure the photon state, right? B now has to measure the photon state that A sends to B. So B has to choose some basis, right? So B has to choose some basis to measure the receiving photon states from A. Okay. Wait, just a minute. To copy a section, copy it. Yes, copy. Okay, fine. Okay. Shit. Wait, sorry. I don't know how to do this. Now it's fine. Okay, so B receives the photon from A. Now B has to measure. Okay, and B has no idea in which state A has prepared the photon. Okay, this all I have written here. Okay, now B will start measuring. Now for measurement, B needs some basis. Now the basis, what basis B will choose now for measurement of each of the photons. First photon, to measure the first photon state, what basis B will choose. To measure the second photon state, what basis B will choose. That's the question. So B will choose randomly. Okay. B doesn't know anything about A, so B will choose randomly. Okay. So B chooses his basis of measurement randomly. Okay. B chooses his basis randomly. So let's see B Bob's basis. Okay. So Bob's basis now, and here Bob's measurement beats. Okay. Okay. So first photon, to measure the first photon, suppose Bob chooses the horizontal vertical basis. So first photon is coming to Bob from Alice. Okay. So this is Alice. Alice, from Alice to Bob, first photon is coming. Okay. And Alice know that he prepares the first photon in DA basis, right? That I can say. So that's here. So Alice prepared the first photon in DA basis, and he randomly chooses DA basis, and he also randomly chooses that first photon is 0, means diagonal. Okay, but B don't know anything. B just receives the photon. B don't know anything. He just receives the first photon. Okay, he just receives the first photon, and B start measuring. And for measurement, B can choose any basis he wants. So B choose, suppose, HB basis, and B choose, suppose B choose the HB basis. Okay, and HB basis, the measurement B do, diagonal photon is coming, right? If diagonal is coming, you can write the state, right? What will be the state in HB basis? Diagonal state is given by, diagonal is given by 1 by root 2 H plus V, right? Diagonal means 0 equals to 1 by root 2, I mean diagonal 0, right? H plus V, right? So B can, and B start measuring in HB basis, so B can get horizontal polarized photon also, 50% chance B can get vertical polarization photon also. So suppose B gets, this is also random, so this is also random kind of thing. So the measurement result we can get, 0 also, we can get 1 also. 0 means we can get H also, we can get V also, right? In HV basis, the diagonal photon is coming, and diagonal photon in HV basis, he can get half of the chance H, half of the chance V, or half of the chance he can get 0, half of the chance he can get 1. So suppose he gets 0, first photon, no problem, first photon measurement is done. Now come to second photon. Second photon, to measure the second photon, B again chooses basis randomly. Okay, suppose B choose HG basis. Okay, and second photon, what is happening to the second photon? Second photon is coming as horizontally polarized, right? Or 0. And if the second photon coming as horizontally polarized or 0, and B is measuring in HB basis, B don't know that second photon is horizontal or vertical. B just receives. Okay, B receives a horizontally polarized photon that A sends, and he measures in HB basis. If you measure the horizontally polarized photon in horizontal vertical basis, then there is 100% chance you will get 0 or horizontal polarized. So this result is certainly 0. Third one, is DA basis, right? Third photon is coming to B, and third photon is what? Third photon is, suppose B measures the third photon in same HB basis. If B measures the third photon in HB basis, what B will get? B will get may 0, or he may get 1, because anti-diagonal is, because third photon coming is anti-diagonal, right? Anti-diagonal is nothing but 1 by root 2 H minus V. So half can be 0, half can be 1. Suppose he gets 1. Like everything is random, okay? Third photon measurement. Similarly, he does all the measurement, okay? Suppose fourth, fifth one, he choose HB, DA, DA, HB, DA, HB, HB. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 photons. So 11 measurement of B is done now. Okay. And he gets the result like this. So your DA is 1, HB is 1, DA is 1, right? Done. 1, 2, 3, 4. 2, 3, 4. Fifth one, HB basis 0 is coming, right? So HB basis it will remain 0. This one HB basis 1 is coming and he is measuring in DA basis, so it can be 1 or 0. Suppose he gets 0. Okay. Then DA basis 1 is coming. He is measuring in DA basis. Sorry, something. 1, 2. This has to be column wise. And 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, 7. 7 number, right? 1, 2, 3, 4, 5, 6, 7. So DA basis 1 is coming. So DA basis he will get 1, right? Then DA basis 0 is coming. In HB basis he may get 0 or 1. Suppose he gets 0. Similarly, you can do the other one. 1, 1, 1. The last one is DA basis 0 is coming and he is measuring in HB basis, so he may get 0 or 1. Suppose he gets 1. Before the last one, like the 10th photon, right? 10th photon Alice is sending as HB basis as 1 and B is also measuring in HB basis, so he will also get 1. Okay, so these are the results B will get. Results of B. Okay, so A sends this 11 photon to B and after measurement this is the result of B. A chooses his basis randomly and E chooses his photon state randomly. Okay, and all this coming to B and B don't know anything about A. Okay, B is sitting somewhere else. Suppose B is sitting in America or something. B don't know anything. B just receives the photon through some channel. Okay, upon receiving the photons, B just chooses his basis randomly and he start measuring, and this is the measurement result. Okay. Now what they do after this? After this, A and B call each other. Okay, it can be public. Okay, suppose press conference or something. Suppose A and B talk to each other. Everyone can know the what they are talking. Okay. After this, A and B call each other. This can be public, so no problem. And sorry, 1 minute just. Okay, so after this measurement of B is done, B then calls A. A and B then talk to each other. It can be public. Everyone can listen what they are talking. Okay. So this is nothing like everyone can listen what they are talking. So this is public. Okay, nothing security needed. Okay, and then they ask each other in call. They just ask each other in which basis they use for measuring the photon states. Okay, so they just ask each other that Alice, in which basis you measure your first photon? Alice tells that I measure in dA basis. B tells that I measure in HB basis. That is the talk, nothing else. Okay, they just ask each other in which basis they measure. Okay, and they keep the result if two bases are same, and they keep the result if two bases are same. Okay, so first call. So first time they ask, Alice asked to Bob that in which basis you measure. Bob said I measure in HB basis. Alice said I measure in DA basis. Okay, so they will keep the result or not? They don't keep. They discard it. Okay, they don't keep the first result. Okay, no problem. Second, again Bob asked in which basis you measure. Alice told in HB basis. Bob also told he measured in HB basis. So they keep this result. Okay, now the result nobody knows, right? Only Alice knows his result. Result means this bits. This bits because only Bob measures his bits and Alice measures her bit. Okay, they just ask in which basis they measure, but the bit they don't ask each other, so nobody knows the bits. Okay, so they are just matching the basis. In the basis they measures the bits. So Alice tells HB basis he measures, Bob tells HB basis I measure. So they keep this. Third one is HB. This is also, but this is DA, right? Third one is discarded. Fourth one is, fourth one they will keep or don't keep. Fourth, one, two, three, fourth. Fourth is HB and it is also HB. So they will keep. Okay. Third one is discarded. Fourth one they keep. Fifth one is HB and DA. This is discarded, right? Am I doing something wrong here? The first one is DA, HB. It is discarded. Second one is HB. Bob is HB. So this they keep this. Third one is DA, HB. This is gone. DA, HB. This is gone. Fourth one is HB and DA. Right. Fourth one is also gone. That's what I'm thinking. Fourth one is also gone. Right. 2, 3, 4. This is gone. Sorry. Fifth one is HB, HB. So they keep this. Right. Sixth one is HB, DA. Right. This is gone. Seventh one is DA, DA. They keep it. Where is it? Okay, go from the last. Last one is DA. Last one is HB. So last one is gone. Okay. Before last it is HP. This is HP, right? So they will keep this. This one is HP and DA. This is gone. This is DA. This is HB. This is also gone. This is DA. This is DA. So they keep this. Okay. So they keeps these results to themselves only. So Alice will keep 0 here. Alice will keep 0 here. Alice will keep 1 here. Alice will keep 1 here. And Bob will keep 0 here, 0 here, 1 here, 1 here. So this is your key. So this is the key. So look, the key is same 0 0 1 1 0 0 1 1. Nobody knows this key except Alice and Bob. Okay, but they don't ask that what is your key. They just ask what is your basis of measurement. Okay, so nobody can know that the key except Alice and Bob. So that is how in quantum cryptography the secure key distribution is done. Now this key is secure, right? Only Alice and Bob will know. So the key is here. Key is here 0 0 1 1, right? 0 0 1 1. This is the key. So any 4 words, suppose any 4 words like frog. Alice wants to send this message frog to Bob. Okay. So then Alice will use this 4-word key 0011 to send the frog. Suppose 0 will keep, maybe the rule is 0 will keep. So Alice tells before that 0 will keep the same words fr. 1 will change O to something else, O to Y, O to X, and Z to Y, suppose. So fr xy everyone can know, no problem. But the key nobody knows, right? So B only knows that the last two he needs to change to O and G. Okay, so that's how this is, you can generate the secure key among you and your friend sitting somewhere very far, like Alice and Bob. Okay, so you just need to call your friend and ask in which basis they are measuring. You are sending some random photons in a random. You choose your basis randomly, diagonal, anti-diagonal, or horizontal, vertical photon. You don't care. Okay, you just prepare your photon state and you send to your friend sitting somewhere else, and your friend don't know in which basis you prepared it or which photon you are sending. He just received the photon and he started measuring the photon state in a random basis. He also choose his basis for experiment randomly, and he just measured the photon state he is getting. Okay, and after your friend is done with his measurement, both of you just call your friend and ask that in which basis you measured. You just both cross check the basis only, nothing else. You don't ask that in first basis what photon state you got. You don't ask this. You just ask the first photon you measured in which basis. If you see that your basis and your friend's basis are same, you just keep the photon state to you, and the photon state will automatically be same for your friends. Okay, just how you saw. You just ask the basis, and if the you or your friend's basis are same, you just keep the photon state to yourself only, and your friend will also keep the photon state to herself also only, and that's how both of you can generate a secure key. That's key your friend will generate is 0011, and you will also generate the same key 0011, and nobody else will know the key. If someone else tries to interfere, tries to know, okay, if someone else wants to know the key, somehow hackers are there, he just measured the first photon is 0. But whenever he will, because of the rule of quantum mechanics, whenever he will try to measure, right, your friend will came to know that something is wrong here, because the hacker don't know that you are measuring in HD basis or DA basis, right? Hacker will choose his basis randomly. Hacker may choose, suppose for this, hacker may choose the DA basis, okay? That is no problem. So hacker choose the basis is DA, and he may not get 0. He will change the state to 1, because horizontal photon is coming. So if he choose DA basis, he may get 1, right? Because horizontal you can write as 1 by root 2 of DA plus anti-diagonal, right? So he may change the state to 1, and whenever he will change the state to 1, you will get to know that something is wrong here, and that's how it is secure. Whenever someone tries to hack, you will get to know, or your friends will get to know. Okay. In general, in quantum cryptography, people will people will not send the 11 photon state. People will send suppose 20,000 photons to his friends, and from 20,000 photons, the key will be suppose 2000 word key. Okay, like this, the cryptography is done. Any questions here? If you have any question, you can ask. If I know, I will try to answer. I don't want to go to the mathematics part, but this is the main idea of cryptography. Okay. Okay. If you have any question, you just ask. Otherwise, we'll move. Okay, fine. The last thing that I just want to tell little bit about the teleportation. Okay, as you see in the questions, right, there is one question, right? This quantum teleportation violates no cloning theorem. It doesn't violate the no cloning theorem. Okay, I told you before, like teleportation and cloning are different. Okay, no cloning theorem tells what you cannot generate an exact copy of an arbitrary state of a particle, right? Both are different. Yes. The question was ki quantum teleportation violates no cloning theorem. Okay. The thing is quantum teleportation don't violate no cloning theorem. Okay. Because in quantum cloning means sorry in engineering, so no cloning theorem tells what? No cloning theorem tells that you cannot make any device, you cannot make any device that can generate an exact copy of an arbitrary state of a particle, right? That is the main idea of no cloning theorem. You cannot generate or you cannot make a copy of an arbitrary state of a particle. That is the quantum cloning theorem tells. Okay, and that is true. You cannot generate or you cannot make an exact copy of an arbitrary state of a particle. And what quantum teleportation tells? That teleportation in quantum teleportation, what we do, we don't generate, okay, or we don't make an exact copy. Here we don't make an exact copy of an arbitrary state of a particle. Here we don't do this. What we do here, we just transfer the state of a particle. Okay, here we just transfer the arbitrary state of a particle. The state of a particle without actually transferring the particle itself. So in quantum teleportation, we don't make some exact copy of a particle state. We just transfer the particle state from one place to another without actually sending the particle. We don't send the particle also. We just send the particle state from one place to another in teleportation. Okay, and this is different from making a copy. Okay, this is just transferring. Okay, we are not making a copy. So that's why the statement is incorrect. Like quantum teleportation violates Nuclear theorem. So this is incorrect. So quantum teleportation don't violate. Okay, this is different. So I just briefly tell what we'll do in quantum teleportation. Okay. So in teleportation, suppose this is Alice again. Alice and Bob, or you and your friend. Okay, whatever. You can take whatever. So this is A. Suppose I tell you and your friend. Friend is here. Okay. And you and your friend share an entangled photon among yourself. Okay. You can generate the entangled photon by, there are some process like parametric down conversion. With this will be some nonlinear crystal. Okay, how you can generate entangled photon pairs? Like you send some laser light or some single, and there is some crystal, suppose BBO crystal. Okay, and it will produce two photons. You send one photon, you get like two entangled photon you will get. Okay, this is called parametric down conversion. There are many things you can just read about this. Okay, by parametric, this is some non-linear crystal. Okay, you just pass the light through this nonlinear crystal, it will be produce two entangled photon. Okay, non-linear crystal. Okay, by parametric down conversion, you can generate two entangled pair, two entangled photon. So that's how you did here, parametric down conversion, PDC. Okay, by parametric down conversion, you generate entangled photon, and you and your friend share this entangled photon. So you and your friend share this entangled photon. Okay, in the polarization basis. Okay, you and your friend share an entangled photon between yourselves. Okay, in polarization basis. Now you have some particle. Suppose you have a particle C. Okay, suppose you have a particle C that is in state psi. Okay, suppose you have a particle C you have a particle C in state 5. Okay, a particle C in state 5, and this particle state you want to send to B. Okay, and the aim in quantum teleportation is to send this particle state send this particle state 5 to your friend without sending the particle. So particle is here, okay? This particle you are not sending. Particle is in state 5. Teleportation, what you do? You send the particle state to Bob or your friend. Here your friend should get the state 5. Your friend should have some measurement device, and upon measurement, suppose this is your measurement operator of your friend. Upon measurement with this operator U, your friend should get the particle state 5. Okay, the measurement with this measurement device, it will give the particle state. Okay, it will not give the particle. Your friend will not have the particle, but your friend will have the particle state. That is what you do in quantum teleportation. Okay, you don't send a particle, you just send a particle state. Okay, so that's why it is told that teleported a quantum state, not a quantum system. Okay, so in quantum teleportation, we teleport a quantum state. We teleport a quantum state like phi, not a quantum system. We don't send a quantum system like the particle. Okay, okay, what is the role of entangled photon? Role of entangled photon, I mean the process, the mathematics you have to do, then you will know the what the role. That I will try to do precisely. Okay, I don't have, shortly I will try to do. Okay, here why you need the entangled photon here. Okay, you need this entangled photon to like send the state, otherwise you cannot send. That is why teleportation is. Okay, so suppose A and B, as I told that is they share an entangled photon. Okay, they need to share this entangled photon, otherwise there will be no teleportation. Okay, so they share this entangled photon. Okay, so they can, so you and your friend can share an entangled state, two particle entangled state, like two photon entangled state, right? Two photon entangled state, and it can be any of the four Bell states, right? You have four Bell states, all the Bell states are entangled, right? They form the basis. So you and your friend can share any of the four Bell states, because Bell states are entangled, right? So this 5 plus minus is 1 by root 2. HA HB plus VB VA. I am writing HV. You can write 0 1, no problem. H means 0, V means 1, nothing. Okay. Yes, we are doing in horizontal vertical polarization basis. Okay. And psi plus, and these are the four Bell states, right? 1 by root 2 HA BV plus minus VA HB. Okay. And you can know which Bell states you and your friends are sharing. Okay. You can also know that by you just do the Bell state measurement technique. I'm not telling the techniques. You just read something about Bell state. This is not this is easy. Okay. Measurement technique. So by Bell state measurement technique, both of you can actually know, like both of you can know which Bell states you are sharing. Okay. Any of the four Bell state you can share among yourselves. But if you want to know which Bell state, then you just do the Bell state measurement and you will know which Bell states you are sharing among yourselves. Okay. Suppose you do the Bell state measurement and suppose you saw that you are sharing the Bell state psi minus. Okay. Suppose I call you, I give the name A and B. Your friend is B. I am calling you as A. So the psi minus AB state will be 1 by root 2 HA VB minus VA HB. So this Bell state you are sharing among yourselves, and you can know this by doing the Bell state measurement technique. Okay. So this state you know, both A and B or you and your friend is know to you. And suppose the particle state phi is given by alpha HC plus beta VC. Okay, or you can write as alpha beta. And nobody knows what the values of alpha and beta are because this is arbitrary. Okay, nobody knows the alpha beta values. Understand? I mean, you don't know the values of alpha and beta, but you just want to share this particle state phi. The particle state is given by this vector alpha beta. Okay, so you can then write the three particle state. Okay, you just write the three particle state ABC, and it will be psi minus AB tensor product with phi C. Okay, and this phi SC you can just write. I think I should copy the thing. Okay, this I'm just keeping the in between. Just multiply the things, and you will get finally this one. Okay, half of phi plus AC alpha VB minus beta HB. Phi plus AC is nothing but the Bell state between A and C. Okay, this phi plus means just replace B with C. Okay, you just multiply and you can write. Okay, just check. Plus half of phi minus AC alpha. I don't want to, that's why I do the mathematics, but I just telling. But main idea of teleportation is what I told. Okay, you don't really need to remember the mathematics. Mathematics is there, you can just check. But okay, the three particle state you can like this. Now you do the Bell state measurement. Now you do again the Bell state measurement. Okay. Now Bell state measurement, suppose A your measurement yields phi plus AC. You are measuring, you are doing the Bell state measurement. So this is the Bell state basis of you and your particle, and upon measurement, suppose you get the Bell state phi plus AC, right? Then the state of B is, this is the state of B then, right? Alpha V beta minus beta HB, right? That you can write like minus beta alpha. So fine. So this is the, suppose upon Bell state measurement you get this Bell state phi plus AC. Then the state of the B, you know that this is the state of the B, right? Then B use the unitary transformation. That's why now B use U as like this. Suppose B state, what B got? B got minus beta alpha here, right? Now B use the device such that U is 0, 1, minus 1, 0, right? Now B use U equals to 0, 1, minus 1, 0. If B use this operator 0, 1, minus 1, 0, then the final state will be what? U into this minus beta alpha. So this is 0, 1, minus 1, 0 into minus beta alpha. And this will give you alpha beta. This is same as phi. Okay. So that's how you can do the teleportation. Okay. We just need to know the state that is collapsing. Okay. Sorry. And we can use this operator upon noticing the state. Okay. And we can get the state of the particle phi. Just you need to do the two Bell state measurement. First, you have to check which Bell state you and your friend is sharing. That then you can know the psi minus. Once you know the psi minus AB, then you can write the three particle state psi ABC, and from this three particle state you have to again do the Bell state measurement between you and your particle. Okay, by doing this you may end up getting phi plus AC or phi minus AC, whatever. If you end up getting phi plus AC, then in your friend's end, first he will get minus beta alpha, and whenever your friend gets minus beta alpha state, he will know that he has to use this operator, and whenever he use this operator, he can get the state. This operator will be different if your Bell state measurement result is phi minus AC or psi plus AC. You can find out which operator your friend needs to use. Just check. So this is the main idea of teleportation. You don't like you don't you just teleport the quantum state. You don't send the quantum system. You don't send the particle. You just send the particle state. Okay. And there is no class of teleportation with no cloning theorem, because you are not generating a copy. You are just sending the particle state without actually sending the particle. Okay, then if you have any questions, just ask. Otherwise, we will end here. Okay. I'll upload the videos and slides in the drive. You can just check. Just read little bit about teleportation. I think I was little fast in teleportation because of time. But cryptography, I think it's okay. But the main idea is like this. You don't mathematics. You may interested, fine. Okay, then bye everyone. I think this is the last class. I don't know.